Hello, can everyone hear me? Check 1, 2.
I can hear you.
All right, cool. All right, so let me share my screen and we'll get started today. Let's see here. Present now. Entire screen. Boom. All right, can everyone see my screen?
Yep.
All right, cool. Just making sure. Thank you, Jose, and whoever else was talking there. All right, so let's do a quick rundown of everything we covered yesterday. Let's see here. So let me know if there's any questions over this stuff as we go too. Are there any questions with the new schedule? How we're doing all that? If you cannot make a certain quiz day or lesson day, just let me know and I can be flexible with that and try to set up a separate time. Very, very flexible with that. Check email often. Practice final. A student recommended that I change the way the practice final looks just so it's kind of like building as we go. So if you go on the website, it actually links. So if you click on the practice final right here on the website, right here, practice final, whoops. It links to this right here, and it's just it's the same problems. I added a couple more and took some out as well. But it's basically like this is the entire first week, and it goes in order. And I also labeled it by section just so it's easier for you to know what's expected of you and that sort of thing. And then any double line just means it's a new week. So the first week is these 5 problems. The next week, which I cut a lot of stuff out because it wasn't actually in the syllabus. And there's no point in testing it, especially if you've seen it already. But the double lines just mean it's a new week for each one of these. The calendar is still the same, though, so we don't really need to worry about that. So sections we are covering, I got rid of some of those. I didn't add anything. And then the practice final just has a different format to it. So that's that. What is this? That's the previous stuff that you should know already. Let's keep going here. Unit 2 is all about differentiation. Remember, that just means finding the slope of a point. So maths of language, translate that when you hear derivative or differentiation. That just means you're finding the slope of a point on a graph if it exists. If it doesn't exist, then it's said to be not differentiable. Okay. Parametric equations, they're all based on some parameter. That's why that's parametric. There's a parameter in there, t, and x and y are defined by that t. They're just separate functions. I mean, they could be the same thing, but they're usually not. And what you do is you do the derivative of one divided by the derivative of the other to find the derivative at any point on that graph. We're not going to worry about the second derivative so much. The next thing we went over was polar differentiation. It's similar to, well, it's not similar to parametric, but it's a different kind of equation where x and y are defined as r cosine theta and r sine theta respectively, and then you do the derivatives and divide those out. It usually involves product. Well, it always involves product rule, which is more of a headache. But hopefully, you've been practicing those. Unit 4 was all about antiderivatives. You can use antiderivatives to find the area of a non-basic shape. So a weird shape, you can find the area of that. Eventually, that's what we're going to be getting to with this whole thing. We went over these formulas for antiderivative of algebraic functions and transcendental functions. Transcendental just transcends algebra, so it's not algebraic anymore. It uses different functions that are beyond the scope of what algebra can do on its own. Integration by substitution, and this was the last thing we did. It's basically just, instead of having this crazy expression on the left here, you can do substitution and make it a lot easier, and then you can use your rules. That's the whole premise for integration by substitution. There are going to be 2 integration techniques we're covering today: integration by parts, which is this formula here, and then integration using partial fractions, which if you hate fractions, you'll probably still hate them after this because it's a lot of fraction work, but I'll try to make it as simple as possible. But before we go on to the new stuff, I want to do some practice problems. So let's see here. Let's do this. All right, so this is everything we covered yesterday, all of this. I did link the solution guide for that practice final, and here's the problems for the practice final right there. But the answers are also in the solution guide. The solution guide, again, everything is going to be on this one page. So I'm going to put everything on this one page on my website. It's linked from Canvas as well. If you want to use Canvas to get to it, that's completely fine. I would just bookmark this though, but that's me. But the syllabus, the online text, the practice final, which is right here, the live lesson sign up. So when you sign up for a lesson, make sure you sign up for your time and when you want to quiz and stuff like that. If you do not show up again, it's totally fine. Ideally, don't take a spot from other people, but this one's done. But you should have signed up for this quiz day here, and then Tuesday and Wednesday's lesson as well. Just note, if you don't sign up for a quiz day, then you're going to have to take that midterm, and that's like or at least part of that midterm for the quiz that you missed. So I am flexible with if you miss an assessment. Just let me know ahead of time. Let me know your plan, and we'll figure things out. What else is here? I did the live lecture from yesterday. The second one actually went better than the first one. No offense to all of you. It was just I didn't make as many mistakes. So if you click this, hopefully it's muted. Okay. It goes through the whole lesson. And sometimes what's good to do with this is if you play it in fast forward, I'm not going to unmute it, but you can hit shift greater than symbol and it does double speed on this. Since you've already seen it, sometimes it's good to just do double speed and just kind of run through it again. That's kind of how I watch all my videos on this. You can also click this little gear and then playback speed. You can do twice as fast, or you can do it even slower if you want to. I don't know. I think that's kind of cool. I'm recording this lesson now, so I'll be putting that link there too as well. And then all the sections, if you notice, I got rid of like all of 4.2. We're not worried about differential equations. You should have seen it in the previous Math 132. It's also not that important for this class necessarily, to my knowledge anyway. So that's why I got rid of it. 6 is going to stay the same. What else did I get rid of? I think I got rid of something with Unit 5 too, but there's a lot less sections than there was before. So that's a good thing. Oh, I got rid of 431 and 432 as well. We're going to talk about them, but you're not going to be assessed on it or expect to know it. It's not that important comparatively to other things. Everything's important, yada, yada. But all right, I'm just going to stop talking. All right, let's get rid of this. Okay, so let's do the warm-up. And these warm-up problems are exactly the same as stuff you would see on a quiz or stuff that you would see on a test. I didn't try to make it where the problems are different, because I hate when teachers do that. So these are the exact same types of problems that you would see on a quiz or a test. This is parametric. Now, it does say I'm not going to give you a physics. This is actually a physics type problem. So you probably have seen this before if you've taken physics. I'm not worried about the physics part of it. I'm not going to assess you on the physics part of it, but the problem itself is pretty good. Basically, let's see here. Let's break this down really quick. Okay, so the position of a particle is moving in the XY plane based on these parametric equations. It says, which of the following points is the particle at rest? Okay, so we're looking at for when the particle is at rest. If you didn't know that already, it's when the derivative is equal to 0. Okay, the derivative of the y and the x is equal to 0. So basically all I want you to do is you can ignore all this position stuff and the particle at rest. You are basically just trying to figure out where is the derivative equal to 0. So you need to figure out, hopefully you can see this. Let me zoom in. You should be able to find the derivative. You set it equal to 0 and solve for t essentially. Okay. So I'm going to give you about 5 minutes to do that now. I'm still going to be sitting here. So if you have questions as you're working through this, then definitely ask. But I'm going to act like this is a regular class where I'd say, here's a warm up. Start working on it. If you have questions, just call me over and I will help you. So if you have questions, just chime in. You can type it in on the little chat thing too, whatever you want to do. I will slowly start working it out, but I do want to give you some time to do it on your own. So if you can get going on that, that'd be great. All right, sorry, I had to check if there's any questions. Any questions or anything? Okay, about a minute left. Okay. All right, so that is time. Are there any questions about anything I did? on this. So first thing I did in the red here is I found the derivative with respect to t and then put that at the top there, just since that's the formula for parametric differentiation. Did the same thing with x. You're dividing it by that. You're setting this equal to 0. I'm not really worried about this denominator, so I just kind of multiplied it over, although it does cause a 0 over 0. But I solved the top part right here, set that equal to 0, and it's equal to, where t is equal to 2. Now, the original problem did say at which of the following x and y, at which of the following x, y, like the coordinate for it. So if you actually wanted to find the x and y for that, all you would have to do is take this t equals 2 and plug it in to this x equation to get the x and the y equation to get the y. So if you actually do that, you end up with -4, 12 as your final answer. But I don't care. I just cared about the t, basically, because that's usually what we're looking for. The rest of it's just algebra. Plugging in this t equals 2 to the equations. That's basic algebra. I'm not really worried about it. Oh, cool. Question. So you just multiply the denominator by 0 to get rid of it. Yes, which technically you're not. I guess you can technically do that, yes. But yeah, that's what I did. For this to be 0, you just care about the numerator being equal to 0 in this case, because it's a physics problem. We don't really need to worry about something not existing, just because in real life things exist. So yeah, that's all I did. Technically, if you plugged a 2 in here, though, you would have a 0 over 0 because it's 3 times t squared. So if t is 2, then it's 12 minus 12 is 0. So it's 0 over 0. But it doesn't actually matter for what this problem is asking. And I will not ever ask you a physics problem like this. This is just a problem I found. I thought it was cool. So wouldn't 0, 0 be a solution? For the x and the y. Well, let's try it out. That could probably work. Let's see here. If your x of t was equal to 0, this means that t would be equal to 0 here. If you put t equal to 0 in this, you would get 12 over 0. So that would not be equal to 0. So x would not work when x would not work if it's equal to 0 because t is equal to 0 just based on that. So I would say no, it does not work. Sorry. Good call though. I like anyone that I always assume I'm wrong. So if you come up with some like suggestion or anything like that, the easiest person to fool is yourself. I kind of live by that mantra. If you know who Richard Feynman is, he was a famous physicist, and he had that quote, and it's just so true. Like, it's so easy to fool yourself, especially when you're a teacher, because you're just like, oh, I've done this for a while, I understand this, but so I always assume I'm wrong and try to like prove myself right. So good call on that. I like the questions. All right, so I'm gonna erase this just because in case people look at this later. All right, here's number 2. Then number 2 is more of a basic problem. It says, what is the slope of the line tangent to a polar curve at a specific value? Also, if you can, please check with your calculator, because I'm going to really try to push for calculator use on that. So you might as well start practicing, act like this is a test. You should be able to do these problems and test your answer with a calculator. So if you can do that, that'd be great. Here's number 2. 5-minute timer. Yeah, we went over these problems yesterday. Do they not look familiar? Okay, there's about 1 minute left. I'm going to start solving this problem out. All right, so first thing I'm going to do is find r prime of theta, which should be 2 cosine theta. All right, from here, if you remember, you need to find your x is equal to r cosine theta, and so you need to find your x prime, which is going to be equal to r prime cosine theta plus r, oops, that minus r sine theta. Something like that. And then your y, I usually do the y first, but that's okay, is equal to sine theta. Y prime is equal to r prime sine theta plus r cosine theta, something like that. Okay, from here, we need to divide. Actually, let's just start plugging in 0 for the, because that usually makes things a lot easier. If we're doing this for theta equals 0, so we're going to plug in 0 for all the thetas here. So r prime of 0 is equal to 2 times cosine of 0. Cosine of 0 is 1, so this is just going to end up being 2. Okay. So then we're going to be doing, so that means this is 2 and this is 2. Since theta is equal to 0, that means this is equal to 0, and then this whole thing is equal to 0 because sine of 0 is 0. So that makes things a little bit easier with the work as well. So dy over dx, the derivative, if you remember, at theta equals 0, you just take the y prime. In this case, if you plug in 0, this ends up being 1, so that cancels out. R of 0, well, here's your R equation. Remember, whenever you're looking for a value, look for the equation for it. It's 1 plus sine of 0 times 2, so it's just going to be 1. So your y prime is going to be equal to 1 because it's just, that's what R is equal to, and cosine theta is equal to 1. Over cosine theta right here times R prime, which is 2. So it's going to be 2 times 1. So your answer should just be 1/2. Did anyone else get that? I logged into another computer, so that way I don't have to flip-flop back and forth. So if you go over here and you see my name, that's a different computer. That's how I'm doing that. Nobody cares. All right, so you want to know x prime and y prime. Okay, so to do that, you need product rule. Okay, so here, let me do this. So if you take this right here, it's the derivative when you have a product is f prime g plus g prime. Ah, that was bad. G prime f. So this is going to be your f, and this is going to be your g. So what I would do is, if you can't do this in your head, like I'm a teacher, so I can do this in my head easier because I've been doing this for a long time. I just set up my f and my g like this, and then my f prime is just r prime, and then your g prime is equal to negative sine theta. And then you use this formula for product rule right here. So it's f prime, that's this. Here, I'll do a different color. It's this times this. That's how this first part came right here. R theta times cosine plus R times negative sine theta. That's why it's a minus over here. You do this exact same thing, this product rule right here with the y, and you get that. Does that answer your question? Sophie? All right, cool.
Can you go over how you got the 1/2, please?
Oh, whoops. Okay. Here, I'm terrible. So this is what we're gonna do. I'm gonna actually go through this whole thing then and write out all the numbers. I'm just being a bad teacher. Okay, so r prime. So this r prime sine theta, the r prime at 0 is 2. So that's this part right here is 2. Sine theta of 0 is 0, so I'm going to put a 0 in here. Plus r where it's 0, which is 1, times this cosine theta, but the theta is 0, so it's just 1. Okay, so this top part right here is the y prime. So that part is up there at the top. The x prime is going to go on the bottom. So this is all going to go on the bottom over here. So r prime of 0 is 2. So I'm going to put a 2 in there. Cosine of 0 is 1. Okay. Minus r of 0 is 1. Times sine of 0, which is 0. Okay. I canceled everything out because there are zeros, but I really shouldn't have done that. I probably should have gone over the stuff a little bit more detail. So that's gone and that's gone because it's 0 times 1, 0 times 2. And then you're just left with at the top 1 over 2. So that's kind of where that comes from. Does that make sense if I break it down a little bit slower like that? Or is it still not working? Oh, yes, thank you. I didn't see that. Okay, cool. Awesome. All right. Yeah, sorry about that. Sometimes everyone's at different levels all the time, and I need to, I don't know. I'm sorry. All right. Let's do number 3 then. I don't mean different levels of like math. I just mean like I talk fast and then I'm doing stuff in my head, and I don't mean anything bad about it. All right, number 3, I'll just do this. It's going to be use substitution. Again, this is a quiz-like problem, so you should you can figure this out. I'm going to give you 5 minutes for this, and yeah. If you forgot the steps, I'll just annoy you by telling you them. Step 1 is to figure out your u. In this case, the u is the most buried function. It's always going to be that for this class, pretty much. So the most buried, whenever I say the most buried, it means like it's like a function that's inside of another function. So look for something with parentheses, or look for something that's like part of another outlying function. For example, that x squared minus 3 is to the 5th power. So x squared minus 3 is its own entity, and then it's to the 5th power. That other variable x is by itself. Like it's not inside of anything else. It's not a composite function. So your u should be x squared minus 3. That's always step 1. Step 2 is finding dx. So I'm going to do that right now, actually. Okay, here we go. So that's our u. So that means this is substituted for. All right, keep going. Don't let me slow you down, dude. You don't have to pay attention to me. To get this dx, hey, buddy. It's okay. So I did steps 1 and 2. I found the u. I found the what substitutes for the rest of it. So actually everything's substituted for because the x dx is equal to du over 2, and then this x squared minus 3 is equal to u. So you can, the next step, so step 3 would be to rewrite everything. Oops, oh no, I just realized I don't want to do this as a definite integral yet. Let's get rid of this. Let's just do antiderivative. There we go. Now we're cooking with gas. All right. Okay, yeah, substitute things in. We still have 2 minutes. I don't want to step on anyone's toes, so let me know if you have questions. Okay, about 90 seconds. Okay, that's pretty much time. Does anyone have any questions? Need any help with anything? We're good with that one. If you remember, it is smart to take the derivative of your answer just to make sure that it actually works. So you would pull the 6 down here. It's also a good practice for chain rule, which you need for this class. Times 2x plus 0. Okay. Let's see here. This would cancel to be 2. This and this would cancel. And you end up with, and then this is gone, x times x squared minus 3 quantity to the 5th, which is the same thing as we got. So that is our answer. Okay, questions on that? Okay, everyone's good at that? That's awesome. Hopefully. Okay, let's go on to the new. Actually, do we need to take a break or should we just keep going here? Hard to gauge since I can't see you or hear you. Anybody? All right, I'll just keep going then. All right, so the new thing we're going over is called integration by parts. You don't really need to write this down just because you'll never be asked to figure out where this comes from. But I do like to show where certain things come from just because sometimes people are interested, like where did this equation, where does this equation come from? What's the thought process behind it? It just seems like it came out of thin air. So I'm going to explain what integration by parts is, but it's used for basically finding integration, like integrals that involve when you're multiplying two values together. Okay, that's usually a sign that, I need integration by parts because integration by substitution, what we just did, that problem we just did, will not work. Okay, so first thing I started with here is the product rule. Okay, this should be familiar to you. This is the f prime g plus g prime f thing. Only I did it for u and v. Most of the time, like your book uses u and v. A lot of times on the internet, or anyone that explains this, they use u and v. So I'm going to be using u and v as well. If you're wondering why don't I use f and g, I'm just trying to use what other people use, just in case you go online and you look up some other resource, and it's just easier if we're all kind of speaking the same language with this. So that's why I'm using u and v. All right, so this is product rule. What you can do with product rule is from here, I am going to do the antiderivative of both sides. Oops, here, oops. All right, sorry about that. All right, I'm just gonna mention the dx here. Remember, you always need that dx. So I have something like this. I do the antiderivative of both sides. Okay, that ends up with, well, this and this is going to cancel. You do the antiderivative. This is going to cancel with the d here. So you end up with uv here is equal to, now if you distribute this dx to each of these things, they're all going to cancel because dx over dx is 1. And then you're going to be left with the integral of v du plus the integral, I'm just distributing this integral to both of these things, u dv. Pardon the noise, I apologize for that. I don't even know how much you can hear it. But, okay, from here, for whatever reason, they choose to solve for this thing right here. So you end up with, so what I'm going to do is subtract this off right here. This I'm going to solve for what I just underlined in green, long story short. U dv is equal to uv minus v du. And you might be thinking, what is all this? It's going to make more sense when we do an example because it is very, very abstract right now. But this is essentially the expression or the formula that you need, equation that you need for integration by parts. Okay, and again, this doesn't really make a lot of sense, but I just want to, unless it does, but like that's fine. But if it doesn't, that's totally okay. We are going to go over how to use this because that's the most important thing. It doesn't matter necessarily like where stuff comes from so much as how to use it. Like you probably don't know how your cell phone works. If you broke it open, it would look like alien technology. Well, maybe some of you would actually know how it works, but it's very complicated. But what's most important is how to actually use your phone, not obviously how it works, because you can get lost in the details with that. So that's basically where it comes from in case you care. Not really that important again, because we're going to be going over how to actually use this formula. So the first example that we're going to do, so this is 414 integration by parts. The first formula the first example that we're going to do using this formula is going to be, what is this? X squared e to the x dx. Okay. So first thing you should notice with this is, can you use u substitution? And the answer would be no. There is no buried function. There's no function inside of a function. U sub works for almost like a reverse chain rule kind of problem. This is not a reverse chain rule type problem. So then we're going to have to go pick another tool out of our tool shed or tool belt, whatever. I don't know what I'm saying. Figure out another tool to use to solve this. And we're going to try integration by substitution, and the light bulb is going off in my head to use integration by parts, because you're multiplying two values together. Okay, so since we're multiplying two values together, I'm thinking integration by parts all day. Here's a little tip for what you should use your u and your v for, because we're going to eventually we're going to use this formula, but you have to figure out what your u and your v are. Okay, your u should always be based on the following. Definitely write this down. Liate. Okay, this is basically the rundown of what you need to use for your u from first choice to last choice. So if there is a possible logarithm, you're going to want to use the u for a log. Okay, right now we have a exponential and we have a algebraic, because x squared is algebraic. There's no logs, so we don't need to worry about the log here. The I is for inverse trig. Inverse trig. There's no inverse trig here, so we don't need to worry about it. The A is algebraic. So algebraic. Okay. Algebraic in this case, there is an algebraic because I just said that a second ago. It's with that x squared. So that means we are going to set up this formula to be u is equal to x squared. okay? Which means your V, or forget about the V right now. Let's just worry about the U. So we have this part right here, okay? The U. It's this. By the way, it's not always the first thing. If these were orders was if the order of this was flipped, then you can't just say it's e to the x. Base it off of this Lie8 method. Okay. The next thing you have to whatever's left is your dv. Okay. That's why I said forget the v. Let's work on the dv right now. Your dv is going to be this whole thing right here. So what I'm going to do is I'm going to write my dv over here. So it's e to the x dx. By the way, some people can do all of this in their head. That's completely fine. As long as you, I mean, not the whole problem, but as long as you, what I'm doing right now, you can almost skip if you want, because you could do part of this in your head, but don't, I wouldn't, but that's just me. But if you do, I will not get upset with you. To keep going with what I was discussing over here, the T is trig. So if there's any trigonometric, we're going to work on those. And then the E is exponential. Okay. So you're going to always want to use that. If you don't do this order, like if I flip-flop the U and the DV here, holy cow, it's a nightmare. Uh-oh, question. Where does the I stand for again? Oh, I'm sorry, inverse trig. Sorry, it's kind of hard to see that. Yeah, it says inverse trig. Inverse trig is like when you have like it's called arc sine or arc cosine. These are the inverse trig ones. Arc tangents, inverse tangents, sometimes they're called. That's the I. Okay, this is a lot. As you can see, this is why I didn't want the quiz to be on Thursday, because you literally have one day to like understand all this and then quiz on it. That seems unfair. So the I is inverse trig, to answer your question. Okay, so now, we have this substituted for here. We have this substituted for. So that means we have this V or this U substituted for. We don't have the V, but we can figure that out from this dV. Same with this one. And then we don't have the du, but we can figure it out from this u. So that's actually what we're going to do right now. Okay, we're going to fill in, we're going to find what the v and the du are for this, and we're going to use this formula. So hopefully this is starting to make sense a little bit. All right, so your du over dx is going to be equal to 2x. Well, we need to solve for du. Remember, I just said that a second ago. We need to figure out what this is right here. So all you do is you multiply the dx over. You just multiply both sides by dx. So this is going to cancel, obviously. Let's do one of these here. So now we have our du. So that's figured out. Awesome. But now, this isn't meant to be tricky, but it could be tricky. We need to figure out what our v is, because we're still missing this one and this one. Okay. Well, you can use this right here to figure out what your v is. So what I'm going to do, and again, people skip this a lot of times. They just kind of do it in their head, which is totally fine. But I'm going to divide both sides by dx for this equation right here. And it's equal to e to the x. I just divided this dx over here. Now to find v, you just, since this is the derivative, you just find the antiderivative. Okay. To find the antiderivative, you do the antiderivative symbol here. Okay. This is getting crazy. This cancels. The antiderivative with this v, this d cancels with this, so it ends up being equal to v. The antiderivative of e to the x is e to the x plus c. We are not going to worry about the plus c for this part right here, so you can just write e to the x. The plus c is going to come out at the very end anyway, so do not worry about putting plus c in there. But now, as you can see, we have everything for the formula, which is awesome. So now we can just fill in what we have there. All right. I probably should stop here, though. Is everyone still on board the ship here? Okay. Cool. Cool. All right. So let's fill in the formula. Yes. Yep. All right, cool. So let's fill in the formula here. Let's go with, I don't even know what to use here. I'll just use purple. Okay. I'm going to write this over here because it got kind of congested in there. So this is going to be equal to, if you remember the formula that's right up here, I'm I'm doing the right side of the formula. The left side was the problem that's given. I'm doing the right side now. UV, so it's just gonna be x squared times e to the x minus v, which is e to the x, times du, which is 2x dx. 2x dx. Uh-oh, we have a problem, and you can kind of probably see why I did this problem. Can anyone see what to do next? This is kind of tricky, especially since you've never seen this before, probably. Any thoughts on what to do next? So we need to figure out this integral right here. All right. Believe it or not, you have to do integration by parts again. Okay, that's kind of why I gave you this problem, because there are certain times where you have to do integration by parts twice. So you have to act like this is a whole other problem and find the u and v and dv and du all over again. So I'm going to zoom out a little bit here. So that's what I'm going to do. What should our u be for this new integral? Anybody? Help me out. Come on. What should the u be? X, very good. All right, well, 2x. Well, actually, I should probably put the 2 in front. Good call. Let's get rid of that. All right, so our u is going to be x, which means our du is equal to 1 dx. Our dv, if the x is my u, the dv has to be e to the x. I already multiplied the dx over. You see what I'm doing there? And your v is once again e to the x. Okay. Now we can do integration by parts again. Do not forget the x squared e to the x, though, because that is definitely needed. So I'm going to drop that down, x squared e to the x minus 2 times. Okay, so now I'm going to do integration by parts for this whole thing right here. Again, it's uv, so x e to the x minus the antiderivative of, and again, that's the formula right here. I'm doing this part right here, this antiderivative part. Okay. Okay, the antiderivative, and it's going to be v du, so it's just the antiderivative of e to the x dx. So you have something like that. Okay. I don't like the parentheses. All right, there we go. From here, now you actually have the antiderivative of e to the x. That's just e to the x. So you get x squared, whoops, x squared e to the x minus 2x e to the x plus 2 e to the x. Now, this is an integral right here, so just do plus c. And then you have your final answer, which is absolutely insane. Whoever came up with this is very, very intelligent. Again, this is like centuries old, this formula, but it's just, you got to admire the cleverness of it because it's just insane. And what you can do if you want, it does take a while, but you can do the derivative of that and see if it all cancels out to get to where you started. Okay, so you should be able to take the derivative of that and get this thing right here where you started, the x squared e to the x. I'm going to do that, but I think we should take 5. And if anyone has any questions or anything like that, you can ask me during these 5 minutes. Okay. All right, so the derivative of this, I have to use product rule for that first thing. So it's f prime g plus g prime f minus another product rule, f prime, which is going to be 2e to the x. I did a minus there because there's a minus there. 2x e to the x plus g prime, which is e to the x times f, plus the derivative of 2e to the x is 2e to the x plus 0. Okay, let's see here. Holy moly. All right, so this 2x e to the x is going to cancel with this. This negative 2e to the x is going to cancel with this, and you're left with this right here, which is what we started with. So we actually did do it correctly. It just takes a long time. But that was because it was double layered. Not all of them are like that. So then I always put right here, I checked it. Okay. So you got about 4 minutes. Let me know if you have questions. I'm just sitting here. Okay, 3 minutes. When you were finding out what V is, why did you cancel out the antiderivative symbol? Are you talking about this right here, this antiderivative symbol? Okay. Here, let me. Very, very, very awesome question, by the way. All right, so let's pull this out here. So if you really think about it, what we talked about before is whenever there's an antiderivative, there's usually a function right here, and this mean antiderivative of whatever's here. So if this was x squared, it's the antiderivative of x squared. There is no number here, but there actually is a secret number that's hidden in there. Does anybody know what number that is? It's a 1. Oh, you just wrote that. Awesome. It's a 1. So the antiderivative of 1, if you think about it, it's going to be 1 v to the 0, because v to the 0 is 1. You have to add 1 to the power and then divide by that power plus c. I didn't do a plus c on that. You don't need to worry about that. So you end up with v to the first over 1, so you get v. So I just kind of did a shortcut by canceling out the d there because it does technically work, but it's just the antiderivative of 1 to answer your question. Very good question. Sorry, I skipped that over. No problem. Are we out of time? 30 seconds. Okay. All right, so the next section, the last thing we're going over today is integration using partial fractions. Okay, so this is another integration technique that we're learning. And the easiest way to explain this is to use an example, like usual. So let's start with an example here. If I wanted to find the I wanted to find the antiderivative of x minus 13 over 2x squared minus 7x plus 3. dx. You should be able to look at this and go, holy cow, I can't really use any of the integration techniques I normally know because nothing will actually work. Even if you tried use sub, I don't actually use sub might work. I should probably pick a bad example for this, but we're going to be focusing on using partial fractions, which is essentially what you end up doing is breaking down this expression right here, this thing right here. So we're going to break this down into what it factors into. So if this bottom part right here, you can rewrite it to factor into this. Hopefully you remember how to factor. That's from like algebra 1, but it was covered in pretty much every calc 1. It's you need it in every calc class, but you can factor it to be this right here. If you need a review on that, I would definitely Google that, but that's algebra. We're not going to focus so much on that. But the factors that break down here, what you can do is they usually use A and B, so I'm going to use a capital A. You can break down whatever those factors are to be the denominators. Oops, that's supposed to be a 2. To be the denominators of a new expression. And then you just have to figure out what A and B are. Now, if you knew what A and B are, you can look at this right now and just go, oh, it's 1 over, or it's A over x minus 3. You need something with logs for that because you have a linear equation on the bottom here. Same with this one. It's a linear equation on the bottom. So you're going to need something with logs on it. But we need to figure out what A and B are. And this is all algebra from here. Okay, to figure out what A and B are, it's going to be all algebra. So to do this, it doesn't mean it's easy, though. It's just a lot of algebra. To do this, what you can do is normally what you would do to figure out what A and B are is you would multiply this top one by this and the bottom one by this. And this top one by x minus 3 and this bottom one by x minus 3. And now if you notice, you have common denominators and you can just add across. We're going to use that fact to figure out what A and B are. I don't know why I'm yelling. Okay. So A times 2x minus 1 plus B, I just did A times this thing right here, and then I'm going to do B times this thing right here, x minus 3. Now, if you notice, the denominators are equal, so we're not really going to worry about that, but these are equal to, it should be equal to this thing right here, okay? Because the denominators are equal, so these numerators, if you add them up, they should be equal to this x minus 13, like so. Oops, can you go back to the bottom of the last problem? Yes. All right, you good? All right, cool. Sorry, I had a message. All right, so is everyone with me with the algebra here? This top part is equal to this top part over here. Or if you don't, speak up. Okay. All right, cool. So what we're going to do here is you can use this to figure out A and B, believe it or not. So we have A times 2x. So it's going to be A times 2x plus B times x. Okay. These things both have x in them. So this should technically be equal to this x right here. There's no other thing for the negative 13 with these x's, so we don't need to worry about it. Okay, now I'm going to distribute over here. So it's A times negative 1, so that's a negative A, and then B times negative 3, negative 3B. This should be equal to this constant right here, negative 13. Okay, this is just all basic algebra with distributing. And I tried to color code it, so hopefully that helps. If you have questions, though, please speak up. Okay. All right. So for here, what I'm going to do is factor out an x for both of these. So you end up with 2a plus b is equal to x. Okay. You can't really divide the x here. I mean, I guess it doesn't really matter. X can't be 0, so that's why you can't divide, because what if x is 0? But what you do know is that 2a plus b needs to be equal to what? Anybody? Come on. No, not x. Close, though. If you multiply this by x, it's equal to x. So that means this whole thing has to be equal to what? Come on, someone knows this. Thank you, 1. Thank you, Karina. So it's equal to 1. Awesome. We can't solve this because there's 2 variables. There can only be 1 variable in order to solve, but you can use systems of equations and solve this thing over here. Okay, let's see here. So let's see, which one should we solve for? It's probably easier to solve for b here. So I'm going to solve for b. So 1 minus 2a. Or maybe it's not easier to do it that way. I don't know. It doesn't matter. All right. So since b is equal to 1 minus 2a, I can write this in over here. Oh, that's not that bad. Like so. Okay. This b is equal to this. So I just substituted it in. Again, just basic algebra. Okay. Hopefully everyone's still on board. All right. Now, since there's only 1 variable with this a here, you can solve for it. That's the rule. If there's 1 variable, you can solve for it. So negative a minus 3 plus 6a is equal to negative 13. Okay, so you have negative 10 over here is equal to 5a, and your a should be equal to negative 2. But we still need b. We have a b equation right here. You plug that in, you end up with 5 for b. Okay, that is not the answer. That's just for what a and b are. Okay, so you still actually have to solve this integral out. So let's go back. Actually, let's do this. So this is equal to the integral of negative 2 over x minus 3 plus 5 over 2x minus 1. Now you should be able to do these integrals without too much issue. You could do use substitution if you want. I'm actually going to show you a shortcut. Since these are both linear partial fractions, you have that x minus 3 and that 2x minus 1. What you can do is just, so this first one here is just going to be negative 2. You can just do ln of whatever's on the bottom because it's linear on the bottom, and then just divide by whatever the derivative is of that x minus 3. Okay. If you did the derivative of this right here, you would have negative 2 times 1 over x minus 3, which is, if you notice, the same thing as, same thing as what we have right here. So if it's linear like this, you can skip right to the ln and then just divide by the derivative. If you don't want to do it that way, you can do use substitution, but that use substitution, you get the same answer and it takes way longer. Okay, because it's a function technically inside of a function here with these things on the bottom. Okay, the next one, you do the antiderivative of this thing right here. It's just going to be 5 times ln of 2x minus 1, but it's all divided by the derivative, that inner derivative of the 2 there. And again, the reason why, if you did the derivative of this, it would be 5 over 2x minus 1 times 2, but you're also still dividing by 2 because it's divided by 2 right here. This times 2 is from chain rule because of the 2x minus 1. So it cancels out. You end up with where you started. So that's a little shortcut. If you want, you can use substitution. Like I said, you get the same thing. Okay, and then it's a plus c because it's the antiderivative, and you have your answer. Probably should clean it up a little bit because this is embarrassing. There we go. And you end up with something like that. That's whatever. Doesn't matter. All right. And you can always obviously check your work by doing the derivative of all this and seeing if you get where you started. We kind of were doing that already as I was checking. So where does the ln come from? Okay, so what I'm going to do, I figured this was going to confuse people because I skipped too many steps. All right, what I'm going to do is I'm just going to pull this part out right here and do this individually so that hopefully that makes more sense. What I'm going to do is take that negative 2 and put it out in front. So it's going to be 1 over x minus 3 dx. Okay, we can't use any rules based on what we have here unless you do that shortcut that I just talked about. So that means you're going to have to do use substitution because technically this is a buried function, this x minus 3. If you rewrote this, it'd be x minus 3 to the negative 1. So that's a buried function because this is inside of this function. So then you need to use substitution. This process does take longer, just so you know. Okay, your u is x minus 3. The derivative of u is 1. Multiply the dx over. Du is equal to 1 dx. Okay, so now if I rewrite this, it's going to be negative 2 times 1, the integral of 1 over u du. If you remember this, and to answer your question, this is where the ln comes from. The antiderivative of 1 over u would be ln u plus c. Okay. Your u is x minus 3, so you have to back solve it in. X minus 3 plus c. As you notice, it's the same thing I have up here. Now, obviously, it's way bigger shortcut if you just realize, oh, it's linear. I can skip right to just dividing by whatever the derivative is. It only works if it's linear. If it's x squared or something like that, it's not going to work. So 2x minus 1 is linear, so I was able to divide by 2. This one I divided by 1. You get the same answer either way. Does that work, Sophia? These take a long time. This is part of the reason why your quizzes are going to be 2 to 3 problems, because it just takes a long time. Ideally, I want like you to be able to solve this in like 5 minutes, but I hate timing because it's annoying. The only thing the only reason most teachers time is because some kids will sit there and look at the test forever, even if they have no idea what's going on, thinking that the answer will pop into their head. But I try to give 5 minutes per problem, which is more than most professors would give. So, all right. That is pretty much everything. If you want to stick around, usually these things they only last like an hour. So that's why it's not like we're done early. I guess we are done earlier than yesterday. But what I want to do with the remaining time is work on the practice test, because the practice test has problems that there's 2 of them that are like this. So if you want to go over those with me, feel free to stay. Otherwise, I will not get upset if you leave. But there are also practice problems online if you want to look through those and start working on those. Some people just leave right away and then they blame me later on for not understanding stuff. I'm literally giving you a ton of help right now if you want it. So if you want to stay, please do. Let's try not to have any excuses. Most of you are engineers or scientists in the making, so got to put the work in. All right. So I'm going to do 5 minutes and then we'll work on the practice final problems. If you remember, the practice final problems are on the website. Where am I at? If you go to the Math 132, hopefully you know where this is by now. Like, I've tried to put everything in one spot. And then just click practice final exam. And again, I reordered it because someone told me to. And right here, you can see integration by parts, integration using partial fractions. It's actually really good to do this one here because it's not linear on the bottom. The way it breaks down is a little bit different. So you're probably going to want to stay for that because it is kind of complicated. Or you can look at my work later on when I post it. But either way, it's complicated. All right, 5 minutes, sorry. All right. Okay, about 3 minutes. Okay, about 1 minute. All right, here we go. People still here? Yes. Okay, so we have this problem right here. Hopefully you can see it. What should our U be? Well, first of all, you have to look. I mean, I know it says integration by parts, but let's like it's a quiz or a test, and it doesn't say that you have to use that. How would you know? Like, what are some signs that it's integration by parts? Anybody? All right, so I'm the worst professor ever here. Okay, 2 different x's. Okay, yeah, we definitely have to use the Lie8 method for sure. There's 2 variables. Okay, there are 2 variables for use substitution though. The main thing is that it's a product. You're multiplying 2 things together. That's usually a sign. I mean, this is very tough. The integration by substitution. Where is it at? Right here. The integration by substitution. If you notice, the derivative shows up. This almost looks like a chain rule answer. Okay. The derivative of x squared is 2x, and there's an x right here. Okay. So this derivative actually shows up in the problem, which is what chain rule is. You're multiplying by the inner derivative. Over here, that doesn't happen. Notice there is no, like, if I do the derivative of x to the x cubed, it's 3x squared. There's no x squared anywhere because it's an x. Okay, so if someone meant that, that is correct. But usually it's a sign when it's just kind of 2 things multiplied together and the derivative doesn't exist anywhere else. We are going to need that Lie8 method, the L-I-A-T-E, to figure out what our U is. So in this case, let's zoom in here. What should our U be based on Lie8? Okay. Remember, the Lie8 is what you should pick for your U first. So what does the L stand for? Oh, ln x. Good. Someone wrote that. So it is ln x because the first thing is logs. If there's a log, that's your U. If there's an algebraic, that's third. There's an algebraic right there. So that's going to be our dv. Is x to the third. You have to have the dx because everything has to be substituted for. Here, let me show you. So this right here is u. So I'm gonna put, now it looks like I'm dividing by u. I shouldn't do that. Okay, this part right here is u. Okay, this part and this part multiplied together is dv. So that means it actually matches what our formula was. Right here we have the u and then we have the dv. Okay. Takes a little bit to memorize that, that's for sure. Okay. Now we have to find our du, which is equal to 1 over x dx. So I multiplied the dx over right away. The derivative of this is 1 over x. This v right here, you have to add 1 to the power because we're doing the antiderivative of that and then dividing by that power. Holy moly. This is a lot. Okay. Is everyone still on board? I should have made you guys do this yourselves here. Should have gave you 5 minutes. My bad. All right. So let's start filling out the formula now. It's uv, u times v. I'd switch the order. It doesn't matter because it's multiplying. I just like the x in front like that. All right, minus v du. Okay, so now you're going to have v times du. Now this is awesome compared to the one we just did before because this x and one of these x's cancel. And we also don't have to do this twice. So now you end up with x to the fourth over 4, whoops, over 4 ln x. Okay, and then I'm going to pull the 1/4 out. And then you end up with x to the third dx. You should be able to do that antiderivative in your sleep. So you end up with, gosh, I hate writing this over and over again. You end up with 1/4 times x to the fourth over 4 plus c. Okay, obviously you can simplify this out to be 16. And there's your answer. All right, preguntas, questions.
So is v just the derivative, or the antiderivative of dv?
Correct, yes.
Okay.
Yeah. And again, I skipped steps, even though I keep saying that I got to work on this. But all right, so if you did, here, let's do this. Let's do this. If I put this over here and I want to figure out what v is, what you can do is you can do the integral of both sides. Okay, if you remember, this is the antiderivative of 1, which is v, because it's with respect to v. This antiderivative, again, you should be able to do that one in your sleep, and you end up getting that part right there. We don't need to worry about the plus c. If you put a plus c in here, some people do that. It doesn't matter because it ends up just coming out again at the end. So that's why I say to wait on that, but it doesn't really matter. Whatever you want to do, I'm fine with. And then someone just asked, does that answer your question, sir? Whoever asked that question?
Oh yeah, we're good.
All right, just making sure. And then Sophia wrote, how would you be able to tell if you needed to use integration by parts again? Okay, so the first thing you always want to do, what I always do anyway, is for use substitution, you look and see, is the most buried function, is the derivative of it somewhere else? So this most buried function right here, the derivative is 2x. Does the x show up somewhere else? It does right there. We just need to divide by 2. That's why I divided by 2 right here to get that x dx. Okay. Over here, you can see that that doesn't happen. Okay, so the derivative, so that means you can't use substitution, but I would always try use substitution first. Okay, use substitution doesn't work. What's next? What's the next tool I can use on my tool belt? Oh, I can use integration by parts. Let's try that. Is it involving things that are multiplied together? Okay, so we have something multiplied by something multiplied over here. There is, so that means a light bulb should be going off in your head. I'm multiplying two things, and integration by substitution does not work. Let's try integration by parts. Now, the only reason I say to do integration by substitution first is because I feel like it's generally easier because students have seen it longer. They might have seen it in other class. If these are both equally hard, then maybe you can start with integration by parts. But either way, make a decision and try to stick to it when you're practicing it. Try to think about what you're doing while you're doing it. So look at this and go, okay, I'm doing integration by parts. The reason why, we kind of went over this a little bit yesterday, or maybe it was with my other class, but you should be able to answer why for every step you do in math. And we don't focus on the why. We like, I'm talking about teachers. We focus on making students be robots and that are just like aimlessly doing problems. I've had students in the past for calculus that don't even understand the derivative they're finding. They can find the derivative all day and use power rule and chain rule, but they don't even know what the derivative is. So they're just kind of like, they're like I don't even know what they're like robots. They're just basically robots, not even understanding what they're doing, but they're just doing it. You never want to do that with math because why would you want to? Well, why would you want to do that with anything really? You want to think about what you're doing and why. So every step that you do, think about the why for it. Why did I pick this for the U? Why did I pick this for? Why is this the DU? Does this actually make sense? Working this out, like you should be able to answer why from every step that I did, from here to here, from here to have. Why did I do that? Or actually, I went backwards this way with it. But why is this here? Why is this here? If you can't answer that, then you really don't understand the problem. You're just going through the motions. And so it is really important to ask questions like that. How would I be able to tell to use integration by parts? The main thing is that you're multiplying two things together, and the derivative doesn't show up anywhere else in a buried function. Okay, integration by using partial fractions is easier to recognize because usually you have some quadratic or something that factors on the bottom. Okay. Also, you can't use substitution on this because the most buried function, the derivative of it, isn't equal to the derivative up here because you need a 2x. There's no 2x here. It'd be too complicated. So that's how you kind of know when it's a partial fraction. You're going to see division. Integration by parts, you usually see multiplication. And why does multiplication set that up? Because it's all based on product rule. Integration by parts is set up based on product rule, so you're going to see multiplication for that usually. Integration by substitution is it's a reverse chain rule. So there's always a function inside of it where the derivative shows up somewhere else. Like the derivative of x squared is 2x, it shows up right there. Okay, and then again, partial fractions is based on factoring, so there usually is something that you're dividing by. And it has to be a fraction, so that's why you're dividing by it. Does that make sense, Sophia? All right. Yes, kind of. Yeah, it's tough. I mean, when in doubt, if you really want me, here's a little tip to hack Mr. Ozarka here is, or you can just call me Chris. I'm not a high school teacher right now. Is if you ever want me to answer a question during an assessment, ask it in the form. I mean, this is just a good tip for life. Ask it in the form of a yes or no question. Okay, where I have to answer yes or no. So it would be something like, do I use integration by parts for this problem? Because at least that shows me that you did some thinking where it's like you kind of think that, but you just need a little nudge by me. Okay, if you went to me during a quiz or a test or assessment or whatever, and you said, hey, how do you do this problem? That's not a good question to ask during an assessment. It's also not good to ask your boss that. Hey, how do you do this, boss? But it is better to say, hey, boss, do I do this? Is this what I'm supposed to do? Show a little bit of initiative. It's just kind of, and people are more likely to answer your questions if they have to answer a yes or no. But if they're like, how do I do this? I'm like, oh man, how do you do this? Okay, now I have to explain exactly how you do this versus me just saying yes or no of what you think you're going to do already anyway. Okay, so when in doubt, try to ask yes or no questions because it puts the initiative. Now, stuff like this is just practice, so I don't really care if you ask a non-yes or no question where I answer with the yes or no. So like her question of how would you be able to tell if you needed to use integration by parts? That's a great question for practice, but I'm talking about for assessments. If you ever have like an assessment that like you're supposed to already know this stuff, when in doubt, ask something where I'd say yes or no, and I probably will be more likely to answer it. So when in doubt, because you wrote yes, kind of, that makes me a little nervous. When in doubt, just ask during an assessment, like, hey, do I do integration by parts for this one? And then I'll say yes or no. And that kind of gives you a hint. Okay. If this was like a longer class than 8 weeks, I would probably be a little bit more strict on stuff because you have more time to memorize stuff, but you don't. So I'm trying to be as flexible as possible. So if that makes any sense. All right. Can we, is everyone good with this problem? Sorry, I always go off on tangents like that. I don't mean to do that. I just, yeah. All right. So let's do the last one then. What time is it? 10:30. Okay, cool. All right, I am going to delete this because I don't need it. All right, this one, partial fractions. Okay, this one is a little bit tricky, but I'll just show you the trick and then you won't be weirded out by it. Okay, a light bulb should go off in your head right away. You can see that there is no, like the most buried function, x squared plus 9. The derivative of that is 2x. The 2x, or I'm sorry, just an x doesn't show up anywhere else in the problem. You have this x squared here, so that would get in the way. Okay, so it also says use partial fractions, so that's kind of nice. Sometimes my tests do say that, like using integration by parts, solve the following problem. So you'll kind of know what to use. But anyway, let's set this up. So this thing is equal to a over, I'm going to factor that bottom part out. I don't know why I did parentheses there. All right. I'm going to kind of take the reins on this one a little bit just because this one is kind of tricky. All right. Now, if you factor the bottom, you end up with something like this. Whoops. Let's finish that out. Okay, the issue with this, and this is not intuitive at all, and I'm really kind of tempted not to put this on a test, but right now it is actually on a test or a quiz, so I kind of have to show you this. This will not work based on what we have here, and the reason why is because if you notice, if I multiply this at the top and at the bottom, yeah, okay. It will not work because this top part, this ax squared plus 9a plus bx squared plus 9b, there is nothing that has just a regular x in it. Okay, this will not work because there's nothing that has a regular x in it, and that is kind of tricky because, like, well, how would this come about if just based on what we have here? The answer is it wouldn't. So what you need to do is, let's get rid of all this. Hold on. Come on, my computer's being laggy for some reason. All right. So the trick on this, and if you do forget this, I will definitely remind you. Just erase this really quick. I don't want it to get in the way. All right. The trick is you have to square this. You can't have twins, long story short, and you have to put an x here, so that way the x actually shows up. You could put an x over here if you want. It doesn't matter because a and b are interchangeable. But the trick is you have to put an x in there, and then you have to square the bottom part. Now there's going to be an x term at the top that you can use. Okay. That is absolutely necessary to do this problem. Okay, from here, hopefully everyone's still on board for that. I don't like tricks like this, but it's not an assessment, so we have to go over it. All right, so we need to figure out what A and B are. Well, B already has the same denominator like there, so I just need to make this have the same denominator as the bottom one, as this one right here. Okay, so now that it's this times this, so it's got the same denominator. So now you can rewrite the A to be ax squared plus 9 plus bx, because now there's an actual x in the problem, is equal to x squared minus x plus 9. So if you think about this, common denominators, if I had to just look at the top, it's equal to the top over here. Okay, is everyone okay with that so far? All right, so let's keep going. Oops, okay. So the x squared right here, there's a 1 in front of it, and there's only an ax squared right here, so that means a has to be equal to 1, which is awesome. That makes things a lot easier. Okay. From here, so it's 9a right here. 9a is going to be equal to 9 because it's the only things that don't have x's in them. So that means 9a is equal to 9, which is great because a is equal to 1 again, so that proves it. Here, your b has to be equal to -1 because this is the only x term right here. In order for this to be true, b has to be equal to -1. So that kind of makes things pretty simple. Simpler anyway. Okay. Is everyone, if you're not on board the bus right now, please chime in. This one actually ended up being a lot easier than the last one we did. Uh-oh. Okay. Which part are you lost on? Sorry.
I kind of got stuck when you put the x by the b. Why is that a valid shortcut? And then I also kind of got lost when you were solving for a and b.
All right. So let's just undo all this then. Here. All right. So the reason you have to put an x there, it's not really a shortcut. You actually have to do it. Like it won't work otherwise, is you won't have an x term here if you don't. Here, actually, you know what we should do? This is going to kill a lot of time, so I'm sorry for people if they need to leave. So if you need to leave, absolutely leave. This will be recorded anyway. You can look at the answer key then. I'm going to solve this problem without putting an x in there. How's that? Does that work? That way, then you'll actually see it not working. I think that'll explain it a lot better. Okay, so let's go with because I remember when I was a student, I was like, I'm going to prove this teacher wrong. I'm going to try to do it and see if it works anyway. And I'm like, oops, it didn't work. So we have something like this. So this is like the normal way of doing it. Okay. If you try to do it this way, again, kind of wrote this last time, but I'm doing common denominators. So we have common denominators of this thing right here. Are you good with that, with the common denominators part? Sophie, are you good with the?
Yeah,
oh, you wrote,
yeah,
yeah.
that's
Sorry,
fine.
I'm sorry, I didn't see it. All right, so now you end up having ax squared plus 9 plus bx squared plus 9 is equal to. Remember, it's supposed to equal to that top part. Oops. Okay. Well, if you put all the x squareds together, it's going to be a plus b x squared because it's ax squared and bx squared. So I'm putting those together here. Plus 9a plus 9b is equal to x squared minus x plus 9. Okay, awesome. Now, based on this right here, a plus b has to be equal to what? Based on this right here. Oh, 1. Someone wrote it. Sorry. Okay. A plus b is equal to 1. Awesome. Okay. So now 9a plus 9b. I'm going to factor out the 9 there. It's equal to 9. Okay. A plus b is also equal to 1. Awesome. That works too. Cool. So that means this is taken care of and this is taken care of. What about this? Okay. There is no x for that. The only way you can make an x be there is if you force it by throwing it in one of those problems like that. So that's where the x comes from. You need something with an x term here in this green, which is based on this up here. And the only way to do that is if you throw an x up there. Otherwise, now you just hit a dead end. You can't solve this problem. Okay. So that's the reason why the x goes there. Now, the reason why the other shortcut works where you have to square this right away is let's try to do it without it. Here, let's do this. We'll put an x here. I can actually just show you right now why it doesn't work without even doing anything extra. If you put an x in here and didn't square this bottom one, this up here is going to end up with an x to the third. There is no x to the third in the problem, so you can't have it where you multiply the top and the bottom by this with the x there. It has to be just an x by itself and then squared at the bottom. You can't multiply the top and the bottom by x squared plus 9. It just won't work. I'll try to take this off the assessment, but I don't know if I'm going to be able to. So that's why you need to do that quote unquote trick. It's not really a trick. You actually have to do it. It's not even a shortcut like you I guess it's a shortcut from going through all this and hitting a dead end. You can't solve for a and b here because there's two variables. Again, you don't have a systems of equations to solve that, so that's why that doesn't work. But, all right, so I should be able to actually delete this. Let's see here. Delete, cool. All right, so now let's start this completely over again, and I'll try to explain that a little bit better next time. All right, so we have x squared plus 9 plus bx, as we said before, and this has to be squared, otherwise you're going to have to the third power at the top with the x, which doesn't exist in the problem, so that's going to lead to a bad thing happening. All right, so actually you should have your stuff written down already. So I believe we said what, a was equal to 1 and b was equal to, what did we say b was equal to, -1? Shoot, does anyone want to help a brother out?
Yeah, it was -1.
All right, cool. Thank you. All right, so now we can rewrite this to be a 1, and then this is going to be a -1, so negative x. So we can solve this part right here. So I'm going to blow that up, put it over here. So you end up with 1 over x squared plus 9. Ooh, that'll be a good review, because I want to remember how to do that kind of problem. dx. So you have two things like this based on the fact that we know a and b. Okay, these are a lot easier problems to do than what we started with because we broke it up. All right, so from here, this one is not exactly intuitive to look at, but you need to set this up to be like it's an inverse tangent derivative. So what we need to do is, if you remember, the antiderivative of 1 over x squared plus 1 dx is equal to inverse tan, or arctan it's called. Here, I'll do it this way. So the derivative of inverse tan is equal to 1 over x squared plus 1. This actually looks like like this right here. The only difference is there's a factor here to make that a 9. So what we're going to do is we're going to factor out a 9 at the top and the bottom. Or actually, we can just factor out top 9 at the bottom. Okay, so you're going to end up with 1/9 x squared plus 1. So now it's actually going to look like, we didn't really do these. Never mind. We're not doing this problem. I'm just going to take it off the test. I give up. Not to be like rude or anything like that, but how many people honestly remember this derivative from Calc 1?
Yeah, no, I don't remember it at all. Because it was taught at the end of the semester, so it was like, just learn it if you want.
It's also really obscure. Like, it's not a thing that you see often, so it's kind of unfair if I expect you to know that for a test, because it's usually one of those things that shows up once on an AP test. So there's like 100 problems in the AP test, and there's one of them. And usually what students do is they take the L on it because they can still get a high score on the AP test even if you lose that one problem. We don't have that because we don't have that luxury because our quizzes are only 2 to 3 problems. So I'm going to say forget this, forget the trick with the X. I won't do any of that stuff. Just making an executive decision because just for the sake of the class. We're grasping at straws here if we analyze and nitpick every little thing. If you're upset by that, I will gladly give you an inverse trig antiderivative problem to do. I am not against giving it to you, but I can give you an easier problem like the ones we were doing previously. In fact, why don't we just do one of those problems really quick then? I will change the thing that takes tests to not have this problem on there anymore. And so let's just do. Let's see here. Let's just find a problem and do it.
Would you be able to unplug your mic and then plug it back in? Because it's super static.
Really?
Or mute yourself. And then, I don't know. It's being weird.
Let me know if you can still hear it after I mute it.
It's not.
I can't hear anything when it's turned off. No, it's just when you're talking.
Okay, so it is my mic thing you're saying. Okay.
Yeah. It was like this yesterday too, so.
Is it any better?
Oh yeah, that's good.
Okay, I'm sorry about
It
that.
got like that yesterday too at the very end.
Yeah, I think there's like a 2-hour limit or something, and it just happened because it happened with my other class too.
Oh, okay.
They just told me to do it, so I was able to. Here, let's pull one from the book. Because the practice problems already have answer keys on them, I'd rather do a problem that we haven't seen yet. All right, so partial. Whoops, don't know how to spell partial. Partial fractions 3.4, page 298. I should just skip right to it. There we go. Techniques of integration 3.4. There we go. All right, let's do, that one's too easy. Let's do, some of them are already factored, which is really easy. Oh yeah, some of them also have 3. I'm not going to give you ones like that, but some of them have 3 factors. You have to use an A, B, and a C for that. Why are these already factored? That's not fun. Let's do this one right here, 199. All right, let's just go over here. We have plenty of space. Something like this. I think this is a fair problem too. It's not overly complicated. It factors easily. All right, first thing that we want to do is break it up. Into its factors like so. Okay. From here, if you remember, you can multiply, whoops. Jeez. You can multiply the top and the bottom here so it has the same denominators. And then now you can rewrite it to be where it's a times x minus 2 plus b times x plus 2 is equal to x. Oh, that's nice. Way easier. All right, from here we have ax minus 2a plus bx plus 2b is equal to x. Okay, so this has an x in it, this has an x in it. So that means a plus b should be equal to 1, right? And then 2b minus 2a is equal to 0 because there is no constant here. These are constants because there's no x's on them. Okay. I'm going to be awesome and divide both sides by 2 here, just because 0 divided by 2 is 0. So now we just know that b minus a is equal to 0, which means a is equal to b. Okay. If a is equal to b and a plus b is equal to 1, that means a has to be equal to 1/2 and b has to be equal to 1/2. All right. So that is just algebra. I haven't done any calculus yet. Is everyone okay with the algebra that I did? Questions on that? Okay, see no questions, so that's good. All right, so from here, I know that this a is 1/2 and this b is 1/2. So what you can do is rewrite all this, knowing that the bottom part there is linear. You can use the little shortcut to be 1/2 ln of x plus 2 divided by the derivative of x plus 2, which is 1. So if you want, you can write divided by 1. You don't really need to, though, obviously, because you're dividing by 1, plus 1/2 times ln of x plus, oops, that's embarrassing, minus 2. Okay, and then it's an antiderivative, so you need a plus c, and there you go. So I will give a problem that's similar to this, because I think that's fair. Any questions on that? And by the way, if anyone like that, I actually don't know who it was, the person that chimed in and said, you know, they don't remember the inverse trig, it was just kind of rushed and stuff like that. Like, if that happens, like, tell me so I can make the tests a certain way to fit how you've been taught, and maybe things that you might not have covered as much. Because some of this stuff is really obscure, and testing on obscure stuff is not fair in my opinion. So whenever there is an issue like that, please tell me. I'm very receptive, or I try to be anyway. Okay.
Yeah, it was just the inverse trig stuff that we didn't really get to, and then like, I mean, the ln(x), like the derivative of or the antiderivative of 1 over x equals ln(x) plus c, like that stuff is kind of new, but that's not that hard. But that's
right.
Like,
I went over that yesterday, so that's why I would say that's
Yeah.
okay to use. I have not gone over the inverse trig stuff at all, nor do I really have time, to be honest. So that's why I want to get rid of that. Like, if I didn't go over the antiderivative of 1 over x yesterday, then I would say, yeah, let's throw that away too. But that's actually really needed for this, so I really can't.
Yeah, no, that's fine. I was just saying the antiderivative stuff, that's just like fresh in our brain. And, like,
I get your point. I was just trying to just explain it. But anything that I can use, like, to be more fair for anybody, just chime in. I'd appreciate it. So this is new for me too, and it's 8 weeks and it's online. It's just, there's a lot of things going against it. Not that like learning face to face is better. I think it is, but some people don't. But just anything I can do, let me know. And then that's pretty much it for class. If you do want to stick around and work on practice problems or whatever, we can treat this like an office hours. I might start doing office hours before class starts too. So if people want to like get here a half hour ahead of time, I'll try to do that as well. Sometimes I do that and nobody shows up and I'm sitting at my computer for a half hour. But so if you do want to come in early or stay later, just email me ahead of time and then I'll plan accordingly. So, all right, that's all I got. If you have any questions, just stick around, or I will see you on Monday. Monday's quiz is going to be over all of this stuff. Okay. Integration by parts, partial fractions, substitution, and then parametric and polar differentiation. So, all right, take it easy.